All right. Hi, everyone. Today our topic is about image super resolution. So this presentation is given by Beilong Tang and me, Mingjing. So this is the outline of our presentation. We begin with the introduction and we give the definition of super resolution and we can look at some applications of it. And then we go to one conventional method, which is interpolation. And then we go to the focus of today, which is the CNN-based methods for super resolution. We will introduce some certain methods in details, and then we will have some more to involve later. So let's begin with the introduction part. So, give this example. And this is very familiar one. And we take the face, which is a subset of this image out, and we zoom in, and we can see this we assume this like image is like 100 times 100 resolution. So it's like not that clear. And the idea of super resolution is that is it possible that we can find a method to increase the resolution, like maybe to this, to 200 times 200. So it became a higher resolution image and it looks better and clearer. So this became the topic of today, super resolution. And given the official definition that super resolution is a class of techniques that improve the resolution of an imaging system. And there are many crucial applications of it. The first one is the medical imaging. So like in the medical field, there are many images like is obtained by like X-ray or some scanning machines. But the problem of it is that it might be not that clear and because of the resolution. So if we can have uh, medical images that have higher resolution, so it can help the doctors that diagnose with the patients and it can improve the like accuracy overall. So another application for it is the video streaming and enhancement and also gaming. So these two are basically the same. It's all about videos. So one essential idea for this application is that it can improve the performance greatly while it do not lose many details or quality. So, and also we can have text recognition and many, many more in the field of computer vision. And as you can see that there are many applications that uses the streaming, which is the videos or multiple frames. But our presentation here will focus on single frames super resolution, which is uses only one single image as the input for process. And so let me introduce the traditional method, which is called the interpolation. So interpolation is actually not a unique idea for the image super resolution, and it's very common in computer science. So the steps in the interpolation in super resolution is that it scatter the image to a new one using that matching the upscaling size. And for these missing pixels, it will take the weighted average of the values of neighboring pixels. So here's an example. So we take the example before that this is one low resolution image and we scatter pixels to a larger one. And we can first we padded this like empty with zero or with black pixels and it will look like this. So and the next step is to we apply interpolation to it so it can become a new one that is like we do not fill in blacks but we fill in colors and it will look like this. And there are many methods. So there are nearest neighbor, and there's bilinear interpolation, and there's bicubic interpolation, and so on. But essentially, these methods, they all use interpolation, and they all uses only the neighboring pixels as the information to produce new data. So there are, of course, a lot of limitations of this method because you can see that compared to ground truth, that the image processed from the interpolation is actually not that clear and it's actually blurred in some ways. So there are two reasons. The first one is the garbage in, garbage out principle that we learned from class that the bad data produces bad data. So we use this like low resolution image as input. So of course we cannot produce very high quality images. And the second reason is that data processing inequality. The idea is that the post-processing cannot increase information because in interpolation, we only uses the neighboring pixels as the information source. So there's actually no external or extra information for it. So the total information are that the same. So we cannot increase anymore. So the idea to actually improve this uh, method is to gain more extra information. So naturally, we can think of the deep learning based methods because we know that deep learning methods, the models itself is a source of data because it learns a lot from the database and it's a pre-trained model. So it itself can serve as a extra information and we can use it for the super resolution for image processing. And now let me head over to Beilong to let me let him talk about the CNN-based methods.
So next, we're going to talk about some of the CNN methods. So the overall framework for all the CNN methods is that we have a low resolution image. Assume we have a low resolution image, we want to upscale it, and we fit into a deep neural networks, right? CNNs or GANs, whatever. And the deep learning is usually learned from a large set of data, which is like training set. Like training set, learn a lot of data set, and we just output a high resolution image. Like just like from the deep neural networks learns a mapping from low resolution data to the high resolution data. And that's just basically the framework. The first paper I'm going to talk about is the one of the very first papers that explore using CNN to do the super resolution. And it has one of the famous authors, Kai-Ming He, who is the author of ResNet, which is the very, very residual network which is used anywhere in deep learning, basically. And this paper is SRCN is originally proposed in 2015. It is one of the first paper that proposes using CNN to do a super resolution. From the result chart, we can directly see that it outperforms the traditional interpolation methods within just a few iterations. For this graph, we only just care about the bicubic one and the SRCN one. So we can see the x-axis is the number of back propagations, and the y-axis is the average test score of PSNR. So PSNR, I think you guys all know it from the homework. It is just like a reverse of MSE. That means that the higher the value, better it will be. And it is widely used as an evaluation metric in this a super resolution task. So we can see within just like maybe 100 iterations, the red line just like is above the blue line. That means that it actually achieves better PSNR scores compared to the traditional methods, and it is improving, and it does better, just much better. So the training details that for the training details, we actually need to think about, for deep learning, we generally think about the data, and it is usually synthesized from high resolution data. So that means that, for instance, for this task, data is easily generated because we already have some collections of high resolution data, target Y. And for input X, we firstly get, we can do it from the target Y. We just downsample from target data to get a low resolution data. And then we use this, and in this task, they actually use a bicubic, they use a bicubic interpolation on the low resolution data to get the upscaled image as like input X. So that makes sure that the key point here is that they make sure the shape of the input X is actually equal to the shape of the target. And for the model, basically, it's just a CNN model. And in the paper, the model is just composed of 3 CNN layers. It is nothing now because of 3 layers is like too small. And the loss function is just an MA's loss on pixel-wise, right? It just calculates the estimated value of each pixel, the MSE loss. And the second paper is proposed in 2016, 1 year later from the SRN CNN paper. And it proposes the sub-pixel convolutional networks. So this paper, ESPCN, it trains the difference between it and the previous one is that it trains CNNs directly on the low resolution data. Recall that previously we first downsample and then we have to upsample. And this paper directly just using the downsample data instead of upsampling. And it proposed a sub-pixel layer to reduce the training cost and computational cost. And we can see from the result that this paper produces much better results compared to the SRCN embedded data set. Okay, then for the SRCN, like I mentioned, the low resolution data image is firstly interpolated to desired shape before the CNN. What it does is like imagine we have a low resolution data, C times H times W. We will first do interpolation to get our desired shape of the high resolution data, for example, C times RH times RW, where R is a scaling factor. And then we feed it the image into the convolutional neural networks and produces the output. So the output will be the same shape as the C times RH times RW. And however, the problem is that the bicubic interpolation is suboptimal, right? For end-to-end training, we want to train every possible parameters on the path. But for this one, we need to use some fixed parameters, which is like the bicubic, which is not trainable. So it might not be suboptimal for the task. So we can just directly replace it with a CNN, right? And also the training cost, since we upsample data using interpolation, so every CNN behind will be influenced by the R square because we operate on the upscale image instead of the original image. And what does the ESPCN do, right? It directly applies the CNN on the low resolution data without actually interpolating it. So what it does is that we have the low resolution data. We have first apply a CNN layer, and then CNN layer will just produce a tensor of shape C times H times W. So the C is actually kind of like the feature dimension, and we then apply a CNN layer to keep increasing the feature dimension to R square. R is the scaling factor. And then we apply a reshape because of we have R square times C, these tensors, we can actually rescale it to type to C times RH times RW. And this reshaped image will just be our target image. So this CNN, the next second CNN producing the R square is called the subpixel CNN proposed in the paper. So let's just do an example of how this reduces the training cost. Assume that we want to upscale image for a factor of 2, and the original image size is 100 times 100. So what we do is that the left part is the model I built using SRCN, simulating SRCN. It has similar architectures with the parameters about 20,000. And for the right part is the ESPCN, and we can see it has an upscaling factor by 2. These two models actually have the same, more or less the same parameters. And for one image, 100 times 100 pixels, we calculate the total, the max stand for the total calculation. You can think of total calculation. We can see that for the SRCN, it will have like 800 calculation. And for the ESPCN, it only have about 200 calculation. So it actually reduces a lot about R square computational cost compared to the SRCN. So it is actually very inefficient in terms of computation. Now I'm going to talk about some loss of this field. So is MSE, so these two papers also use MSE. So is MSE a good loss? And this image actually shows MSE circle, basically says that every image on this circle has the same MSE loss compared to the reference image. We can see that some images does not look very good, right? So in fact, MSE might not be good because in computer vision, because it loses the structural information, right? It will calculate the pixel wise, but it doesn't calculate the variance, basically the variance of one image of the target image. So there are some alternatives. The two alternatives, one is called using a lot of loss, which is called SSIM loss. It is widely used in computer vision to replace the MSE loss because it considers the structure of the upper image itself besides the MSE. And also people use this loss called VG19 loss. Basically, people have trained two networks and they just use the loss between the two networks. So I'm not gonna talk about VG19 loss, just SSM loss. So for SSM loss, I'm gonna just like throw out the formula from Wikipedia because I think it is kind of straightforward. And you can see for formula, right? There are some like the definitions we can see, but the only thing is that for the theta x squared and theta y squared here, it is a sample variance of x, y. So what does it mean? That is that it actually considers the variance of the sample. It cannot be too noisy or like not be normal. So it is this is what SSIM does. And so lastly, I'm gonna just like dive briefly introduce some like other CNN style method because CNN is not so widely used because there are better structures. The first one is the GANs, also called the generative adversarial networks. Basically, they train two networks against each other. One network produces the upscale image, and the other network takes the input of the upscale image and try to see, oh, if it is generated or real, and they just train against each other. I'm not going to talk about details, but they actually utilize the second against networks is the discriminator. They actually use the discriminator loss as an actual loss. other than the MSE and SSIM loss. So there are papers, for example, like SR gain, the ESR gain, etc., etc. But now what's widely used is since because of the computational power increasing, people actually use the attention mechanism, right? Directly apply attention using some striding windows to get result. So I think that's all what we are going to talk about today, and thank you guys for listening.